Today we're going to be going over a combined spectral problem in which we investigate the IR spectroscopy, the carbon-13 NMR spectroscopy, and the hydrogen-1 NMR spectroscopy for a certain molecule. In this case is C6H12O2. Now we don't know the shape of that molecule at this point, but we do have its molecular formula and three forms of spectroscopy that can be used in order to determine what the molecule specifically is. So among these three different types of spectroscopy, we're going to start with the IR infrared spectroscopy. So that's going to be down here. This is the IR spectroscopy, which is incredibly helpful for determining functional groups that are present within the molecule. It's not going to necessarily help us figure out the ways in which the carbons and hydrogens and oxygens are ordered, but it will help us determine the functional group. So we'll start with that. IR, you have your x-axis, which is the frequency labeled as your wave number in inverse centimeters. And on your y-axis, you have the light absorbed, which is labeled as percent transmittance right here. So carbon-carbon bonds are not usually nonpolar and are not going to show up as peaks in IR. So what we're looking at mostly is carbon-hydrogen bonds and the carbon-oxygen. We'll start here at the top. At this 3000 mark, this is going to be denoting a sp3 hybridized carbon-hydrogen bond group. So you can see here we have this tall peak and nothing past 3000, which is where we would get into the OH, the oxygen-hydrogen bonds. So we can go ahead and just immediately rule out any functional groups that contain an oxygen-hydrogen bond. Our next peak down we have at about 1700 inverse centimeters, which is going to be marking a double bonded carbon oxygen. And then as we continue down, we have our next highest peak is this carbon oxygen bond, which is around 1200. So we know that we have, from our molecular formula, we know that we have two oxygens. So it looks like one of them is going to be double bonded and one of them is going to be single bonded. And then we do not have any oxygens bonded to a hydrogen. So right off the bat, it looks like the functional group is going to be an ester. We thought maybe carboxylic acid, but because there's no OH bonds, we can rule that out and say the functional group is likely an ester of this molecule. So the next thing we're going to do is we're going to come up here and we're going to look at our carbon-13 spectra right here. So in carbon-13 NMR, we're looking at NMR specifically is the nuclear magnetic resonance spectroscopy. So it's looking at specifically the carbon-13 isotopes, and it can tell us a lot about the behavior or the makeup of the carbons in the molecule. So we have our range from 200 to 0 parts per million. So here we're looking at each peak is going to represent unique carbons. So 1, 2, 3, 4, 5. We have 5 unique types of carbons on this molecule, which means there are going to be 2 carbons, since the molecular formula is C6. There will be 2 carbons that have the same, that are analogous within the molecule. So we'll start over here at 175 or so parts per million. This peak over here is within the sp2 area of the spectrum. See, the sp2 area sort of starts around 90, almost 100, and then goes up to about 200, whereas the sp3 is those smaller numbers. So this peak right here has a sp2 hybridized carbon, which is double bonded to an oxygen and single bonded to another oxygen, and that is sort of in agreement with the idea that we have a ester as a functional group in this molecule. It also is reinforcing the idea that those oxygens are going to be connected to the same carbon in this molecule. So as we move further down, let's look at the sp3 hybridized carbons that are in this molecule. First of all, around 60, we have an sp3 carbon-oxygen bond. So that is going to be a carbon bonded to this oxygen right here. There's going to be another carbon coming off of it. And then as we come further in, this 40 to about 0 range is where you see your carbon-carbon and carbon-hydrogen bonds. So it looks like we have 3 different types of carbon-carbon or carbon-hydrogen bonds here, the degrees of unsaturation. So in order to calculate our degrees of unsaturation, we're going to multiply the number of carbons we have, add 2, subtract the number of hydrogens we have. If we had nitrogens or something akin, we would then subtract those as well, but we don't. So we subtract number of hydrogens and divide it all by 2, giving us 1 degree of unsaturation. So that means there is one spot in this molecule where there is an unsaturated carbon. We're going to say that that is likely from this carbon-oxygen double bond. Now we're going to go ahead and look at the hydrogen NMR spectra. So let's come down here. Your hydrogen NMR is going to be telling you a bit about how the hydrogens are interacting. In here we have, again, we'll count the number of peak groups that we have in order to determine how many unique hydrogens we have. So we have 12 hydrogens total, and we have 1, 2, 3, 4, 5 separate sets of peaks. So we have 5 unique types of hydrogens here. So you'll see these numbers at the bottom that I have marked off, 4, 3, 6, 3, and 3. These are marking what the multiplicity of each peak is. So as it has multiple peaks, if you subtract one peak, 1 from the number of peaks you have total, that's going to give you the number of neighbors the hydrogen has. So for a quartet multiplicity, it's going to have 3 neighbors. A triplet multiplicity is going to have 2 neighbors, and so on. And then these numbers up here, 2H, 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 3H, 3H, that's how many hydrogens of the molecule have that behavior. So 2 of our hydrogens are going to be around 4 parts per million, and that is marking the hydrogen right here, CH2, of a hydrogen that is attached to a carbon with an oxygen as a neighbor. We have 2 hydrogens that are attached to a carbon that neighbors a double bonded oxygen carbon pair. So right here, these 2 hydrogens are right here. So over here we have 2 hydrogens with 5 neighbors, see, that are going to be bonded to a carbon hydrogen pair on each side. So we have on one side it's going to be a carbon CH3 likely, and the other side it's probably going to be a CH2 in order to have the 5 neighbors total. Next we come up here, we have 3 hydrogens that have 2 neighbors. That's going to be our CH3 on one end, and then the other side we're going to have our CH3 on the other end of the molecule. So it looks like it's going to be a linear molecule versus something like a aromatic ring. If there were to be any peaks up here in this higher end of the chart, that would be denoting carbon-carbon double bonds. This right here is incorrect, this question mark. This range would be denoting any carbon-carbon double bonds with hydrogens attached, or any carbons that are bonded to, any hydrogens that are neighboring a carbon that is double bonded to an oxygen, and that's it. So something more similar to a aldehyde or a carboxylic acid versus the ester. So knowing all of these things, let's go down and look at our charts. So here we have our molecular formula, C6H12O2, and our degrees of unsaturation being 1, which means we have 1 double bond in that. Our IR we went over, we have, this is where we determined what sort of functional group we have, which we believe we're working with an ester here. Down in our NMR spectroscopy, we again have our chemical shifts, which is our x-axis values, and then using that information, we were able to determine the bonding environment or the interpretation. So this is what we discussed when we were going over the carbon-13 graph here versus the hydrogen graph here, which is where we saw the distribution of hydrogens, the types of neighbor environments they have, and what that meant as a whole. So using all that information, what we have, our final proposed structure is a propyl propanoate right here.